Now, because with the geometry of the Earth, if you had to put something between the Earth and the Sun, you just need to block the disk area, not the whole spherical area of the Earth. And so now we're talking about 2 million square kilometers. Still rather large structure if you're going to build a structure like that out in space. So, you know, I mean, my basic point is I think this idea of building this out in space is not really practical. And whereas I think this one is eminently doable. One of, you know, just to be a little disorganized in this talk, the geoengineering has been proposed to play at least two kinds of roles. One is sort of as somehow a replacement for CO2 emissions reduction. And the idea is that, oh, if we want to limit ourselves to some amount of warming, that we can continue emitting more CO2, and then you try to geoengineer the planet to reverse that. And another view is what I'm presenting this as is some kind of emergency response system that if something really catastrophic happens, that you'd take these desperate measures. And this idea of building something out in space of this size would take a long time to do, whereas I'm going to argue that you could put particles in the stratosphere very quickly. And so this, I think the space-based options won't really work as an emergency response system. To give you an idea of how fast you need to build these things, so we said each doubling of CO2 in the atmosphere traps 2 times 10 to the 15th watts. If we say this doubling is occurring on the century time scale, then that means that the radiative forcing from the CO2 is increasing at 2 times 10 to the 13th watts per year, which is okay, about twice or somewhat more than the total energy consumption by mankind. And so the rate at which this radiative forcing is increasing is 600 kilowatts per second. And so if you wanted to match this with geoengineering, you need to block another 600 kilowatts of incoming energy every second. And you know, I won't go through dragging you through all the calculation of the numbers of it, but you know, if you wanted to do this with the space-based option, you'd need to build 54 square kilometers of satellite a day, which is you know, more than a square kilometer every half hour, and that's just such a Herculean undertaking that you know, I would say it's just easier to transform our energy system, and so I think the space-based options are interesting to think about, but not really practical from either an emergency response system, or even if you just want to avoid, it doesn't seem an attractive alternative to avoiding CO2 emissions. On the other hand, you'd think, okay, because the stratospheric system is working on the whole surface area of the Earth, you need 4 times as much area because it's not just the disk area. And so, well, if we needed 54 square kilometers for the disk one, we're going to need over 200 square kilometers a day or for this system, and isn't that worse? And the answer is that it's not really worse, and small, let's just do the spherical area, that if you want to get particles with an area of 8 million square kilometers, and you make them out of 0.1 micron particles, which happen to be the best size particle for this process, that 0.1 micron particles that would have an area of 8 million square kilometers would be a cube only 100 square meters on a side. So basically, if you could take a cube of 100 meters by 100 meters by 100 meters, grind it into 0.1 micron particles and loft it into the stratosphere, that would be the right amount of material. Now, I'm oversimplifying because the radiative properties of particles don't follow simple geometry, but just this is the right order of magnitude. And this is less than the amount of material that Mount Pinatubo, which was a volcano in 1991, put up in the stratosphere. And you know, we could basically do the same kind of thing and put you know, a cubes, 100 meter on a side cubes worth of material into the stratosphere, and that would be more or less enough to compensate on a global mean basis for a doubling of atmospheric CO2. I meant to update this slide. This should be more like 30 years for 50% in the atmosphere. There's a time issue here, in that if you drive a car home today, that about a quarter of the CO2 that comes out of your tailpipe today will still be in the atmosphere 1,000 years from now. And so if you expect to reverse the effects of CO2 release by geoengineering it, you have to set up some kind of institution that will last a mighty long time and be able to compensate for future emissions. So to compensate for 1 ton of CO2, which each ton of CO2 released blocks around 600 watts additional radiation from escaping to space. And so you'd need sort of an equivalent of disk area to block 0.6 of a square meter. And then say 30 years later, this should be updated, about half of it would be in the atmosphere. Maybe 50 years later, half of it would be in the atmosphere. You'd still have to block roughly 1/3 of a square meter. In 1,000 years, this, a 1/6 of a square meter or so. And so anyway, so there's a long time commitment to CO2, and geoengineering systems don't have intrinsically that same long time commitment. So I'm not, I'm more of a climate scientist than an engineer, but there was a 1992 National Academy study that looked at different ways that you could place particles in the stratosphere. And, the quickest thing seems to be taking a jet airplane up and releasing particles out the back of it, or the other thing is to use high sulfur fuels, and there's various airplane-based systems that could be deployed pretty much right away. There are other ideas, like a balloon-supported smokestack to the stratosphere, or a hose, essentially, that the Department of Defense looked at. And the thing is that all of these things look like they would cost in the low billions of dollars, where the cost of energy system transformation is thought to be in the high hundreds of billions of dollars. And so economists who look at this in a purely economic way and believe these systems will work, that the cost, that it looks a lot cheaper just to try to geoengineer the planet than to reduce carbon dioxide emissions. Of course, it's far riskier. So one of the basic things of geoengineering is that if you look at the radiative forcing, or the heat trapped by adding CO2 to the atmosphere from a doubling of CO2, this is seasoned by latitude. So this is the South Pole, the North Pole. And that you see it's more or less 3 to 5, about 4 watts per square meter over the whole Earth. And it's relatively uniform, both seasonally and latitudinally. Whereas if we look at, and then if we were to turn down the sun by an equivalent amount, we would see that, well, the sunlight is mostly at the equator, it's mostly at the high latitude summers, and so that a reduction in sunlight looks nothing like the pattern from CO2 forcing. And so why would you, if you trap this much heat and then reduce this much sunlight with these different patterns, wouldn't you expect to have different residual regional climate change? And this is actually what, when I started doing this work, I thought it would never work, because I'd say, well, how could the climate effects of this change counteract the climate effects of that change? And we did a number of simulations. Here's more recent versions of them. And so this is a 2-time CO2 simulation using the NCAR community atmosphere model. And here's with a 1.8% reduction in sunlight. It needs a little more because of some feedbacks. And you can see that over most of the planet, it does a really excellent job. And if you look at the seasonally, it's doing a pretty good job seasonally also.